Okay. Share my whole screen, so I want to show you a simulation online. All right, so I'm in this page in that packet. If you did come and get one, or if you printed one, I'm on page 25 in that. And I'm really only going to talk about this graph down at the bottom. We've covered all of this up at the top. You can read, but I do want to talk about the temperature dependence of this graph. So we recognize hopefully this graph. It's called a Maxwell Boltzmann distribution, or just a Maxwell distribution. And we looked at this a few different ways. One was through temperature, and then one was through molar mass. So over here on this one goes, sometimes it's number of particles. Sometimes they do a little statistics on it, and they call it a probability distribution, which is what this graph is going to do. And generally we have down here energy. This one has speed, but speed is directly proportional to energy. Here's what I want to show you. Now this is energy. So at some point we could identify the activation energy for a particular reaction. And let's say it's at here, whatever that value is, 100 kilojoules for the activation energy. So that means in order for a particle to possess enough energy to make a reaction happen, remember they have to collide, and they have to collide with enough energy to overcome the bonds. And so let's say right there is the activation energy. Now this is the general shape, or even better yet, let me use this. Well, sometimes I print this stuff and then I just start talking and I forget. All right, so let's say it's right there. Right there is the activation energy. So the EA activation energy. Let's say what it would be, like about 550. Now this is in speed, but let's call it kilojoules with cheat. All right, so you can see very few particles at this temperature. So this is at some temperature. Very few particles possess enough energy to make this reaction happen. It would only be the ones that are higher. So particles that possess energy higher or equal to the activation energy, that mark right there. All right, now why does that matter? What happens to this graph when you increase the temperature? Remember what I told you about the halfway point. So right about here, or really close to there, is the mean, the average peak. Now it's a little bit different because you can see this side of the curve, the right side of the curve is a little bit skewed. It's not a perfect bell curve, but it's pretty close, pretty close. So right now the average energy then, or the average kinetic energy, or the average speed, or the average temperature, whatever you want to look at it as, is right there. So temperature 1. But let's say temperature 2 is greater than temperature 1. So what happens to the shape of the graph? So that's what I want to show you with this. So here is that same graph, but now I can manipulate the temperature. So you can see I said right about here, I can't write on this now because I'm going to manipulate it, but right around, pay attention, about 550, somewhere around right there. So you can see my cursor. So somewhere right around 550, we said that's the activation energy. Watch what happens when I change the temperature. So I can grab this slider right up here, and I can increase the temperature of this gas. So now if we're looking once again, if I put my cursor back here at 550, now look at all the particles that we have that possess enough energy for this reaction to happen. So changing the temperature does not change the activation energy. Key phrase there. Change this. So changing temperature does not change the activation energy. Well, then why does the reaction go faster at higher temperatures? It goes faster at higher temperatures because here's that temperature, here's the activation energy we needed, 550. Now, when we look at this one at a higher temperature, here's the activation energy we needed. So at a higher temperature, there are way more particles, or a higher percentage of particles possess enough energy for the reaction to happen. So one thing that we need to add to this then is, what about a catalyst? Because a catalyst also speeds up the reaction. So a catalyst also speeds up the reaction. How? A catalyst does affect the activation energy. Remember, that was the definition. It provided an alternative path. So if we're looking at these graphs, reactants to products, what it did was, remember, it provided an alternative path, maybe 2 steps like this one, where the reaction would occur faster because it lowers the activation energy. So now, instead of changing the big graph, if you add a catalyst, it shifts this line maybe to 400, let's say. So now without changing the temperature, you have more particles that possess enough energy to make the reaction happen. All right, so that's what today is all about. So try what I gave you today, and as usual, just give me a message if you don't know what's going on.